Hello. So good morning, everybody. And so we are from Mahindra and Mahindra Group. My name is Neha, and with me I have my colleague Nihant. So we would be taking you all through some of our work which we are doing in the AnyLogic software. Here, for I will just start with explaining about how the sequence which we go. First, we will brief you a bit about our Mahindra Group, and then Nihant would progressively take you through what work we have been working on, the model, and as well as the expectations out of it. So to start with, we thought that it would be great if we can introduce ourselves and the organization we are associated with. So we both represent Mahindra and Mahindra Group here. So Mahindra is an MNC, Indian MNC. It has a lot of business verticals which deal in automotive sector. We have agri business with us. We have two-wheeler. We are also in engine manufacturing. We supply a lot of integrated parts to defense, Indian defense, ministry and systems. We are also into finance, IT, tech. Mahindra Group is also a part of M&M Group. So it's a very large conglomerate. It's like the revenue in FY25 was approximately $25 billion. And within that Mahindra Group, basically we are a part of team which is called Auto Digital Center. And within ADC, that's the short form for Auto Digital Center, we are aligned with a lot of, almost all the R&D centers which cut across these business groups, basically. From that auto centers, what we are dealing with is we represent manufacturing IT team here, and then our team, so we are not just into work. You can see the team pictures having fun as well. So we represent digital manufacturing team COE over here. Moving on to like just a quick brief about what all team works with. So I lead this team, and Nihanda is my colleague, who is part of the team who takes care of discrete event simulations. That's our point of interest. But apart from that, we do also work for delivering MBOM, that manufacturing and engineering BOM solutions across verticals. We work on factory layout, like we have a walkthrough of almost all our body in white and TCF facilities. And if it interests some of you, right now also we are speaking from one of our largest manufacturing facility from India. So Chakan, Pune is the location where we both are, representing Mahindra from. Apart from 3D factory layouts, we also work a lot on virtual reality, augmented reality, mixed reality stuff. We do a lot of digital mockups, which is nothing but process simulations. And we also do process planning solutions delivery from this team. So right now, for discrete event simulations, we have approximately 20 to 25 projects that we cover annually, and which cater to a lot of problem statements around logistics, assembly, sometimes even outbound logistics, which Nihant will cover, plus how it has to be mixed up or carried over to inside inbound logistics. So that will be a point of interest. So in this specific project, which Nihant would be kind of taking you through more technically. So I'm her his manager, and I'm more into project management. But Nihant is very much apt in the discrete event simulation parts. So here the project that we are going to share with you is for a facility at Haridwar location for M&M manufacturing plant. And then this particular project caters to truck turnaround time. That is called like truck TAT, that's what we generally call. So basically it concerns with the logistic infrastructure, which has docks, gates, and there are several cycle times which is associated to a particular material. So currently Mahindra Group is seeing a lot of growth, and we have a lot of new capacity plans, and Haridwar plant is one of them, which will see a mix of product types, like shifting from Pune location to over there. So how discrete event simulation specifically done in AnyLogic will help the plant in planning the logistics in a better way, utilization of docks also in a much progressive and better way, and how to handle the upcoming capacity, which will call for a very unique product mix that we will cover in this model. Yeah. So over to my colleague Nihant.
Thank you. Yeah. So, as Neha rightly said, we'll be looking at how we have leveraged AnyLogic as well as the whole discrete event simulation to see how we tackle this problem of, these issues of truck turnaround times at our plants. So here we can see, like she also gave an overview, like we are not sure whether our existing infrastructure would be able to handle the capacity enhancements or not. So, and it is also important to note that M&M uses a just-in-time and just-in-sequence inventory management. So what I mean by that is like we rarely store like items like materials in the plant. Like we don't have a significant, like we, let's say there's no warehouse in our plants like where we can just go quickly grab whatever items we need at our lines. So what we do is like we have a sequencing in place, like a scheduling in place, where when the item is needed, the orders are automatically sent to the supplier end, and they send their delivery trucks containing these materials straight to the line, and they arrive just in time. Hence the name. So I will tell you why this is critical later on. So we can go ahead to the next slide. So here we have our objective and goal. So a goal, like we said, we need to create a model in AnyLogic that should be calibrated with our real life scenario, and this model can then be used to test out future scenarios, like whether it be increasing the number of docks, like basically optimizing the route, or like increasing the infrastructure, changing the infrastructure and whatnot. And we should also be able to identify any traffic areas in the plant or congestion areas in the plant, which can lead to higher takt times for our trucks. So I'll just demonstrate a basic video over here. So 1 second. So this is like a sample like video, like demo, showing how the process flow has been defined for this plant. So we can see that the trucks are entering from over here. And this for our use case, there's only one entry and one exit, and that's at one location. So the trucks come in, and the process flow has been defined, the path has been drawn, and they will, yeah, that's okay. So they will follow the exact process flow of like entering, reversing, and reversing into the dock and everything. So there can be another approach where we could have just given a delay for all this reversing and whatnot, but I wanted to make it as accurate as possible. So I have defined each and every step of the truck, like the path. So yeah, going ahead here, we can see that the truck, as per the process flow of what is happening currently in the plant, we have defined it. So the truck is reversing all the way back, and he's then straightening it out and then heading towards the exit gate. Yeah. We also have made simple charts where we can see the current dock utilization. So right now this is running at a like virtual speed, like a high speed. That's why the utilization times are changing very quickly. So yeah, going on to the next slide. Okay. So first, we'll talk about trucks. So how are we modeling the trucks? How did we model the system? So we have a system called VTS, vehicle tracking system, that automatically logs the truck in and out times and the dock in and out times in our plants. So this system, we were able to retrieve the data which we needed to, base the model out of. So we have several parameters like unique ID of the truck, and let me get my laser pointer out. So we have the unique ID of the truck, plant in time, dock number, dock in time, and dock out time. This is based off our past data, like currently what data we have. And the trucks are scheduled in the model to get generated at the plant in time. Now, at if in case the truck is generated, like only if the dock is free will the truck proceed, like inside the plant. Otherwise, the truck must wait outside the plant. So we have this assumption, and the next assumption is that only upon reaching the dock will the loading and unloading start. I mean, it's pretty obvious, but how we got this tab times is that we have the dock out time and dock in time, and from that we have derived the tab times, like the unloading and loading times, the amount of time the truck must spend at the dock. And also we have also defined the speed. Average speed is 5 kilometers on straights and 2 kilometers on curves. We also have another kind of movement, the trolley movement. Now, trucks are just one thing, right? So they bring in the materials from suppliers, from like other suppliers and everything. But we also have a trolley movement. Now, what are trolleys? So trolleys, they carry our, for instance, in this case, they carry our BIWs and various other child parts, the bumper and all that. So they come from another gate, which I will show you in another upcoming video. So they enter through another gate, and they have a separate process flow defined for them. So I will show you a demo later on. Now, so these are the data points which we get from the trolley side, which was provided by the logistics team. So we get the destination, like where they need to go to once entering the plant, number of trolleys that enter at a time, the start time per trolley length, and trip repeat interval, like how often do they keep entering into the plant. So they use a separate gate for entry and exit. The end time for all the movements are 5:05 p.m., post which there won't be any trolley movement at all inside the plant. And they must be given priority to pass if in case there is an obstruction, as we need to consider them more critical than anything else, like a truck, for instance, like carrying something. So there are four different kinds of trolley movement present in our plant, which we have defined for our model. And from the end user, we have also noted that they are the main cause for congestion in this plant, as like there are multiple of them, and they are much more frequent than our trucks. So once again, we have given the speed 4 kilometers on straights and 2 kilometers on curves. Now, this is our input data format. So it's pretty simple. So we collect the aforementioned parameters in the form of Excel, and the end user is able to input his data in this format in the Excel. And what AnyLogic does is we have configured the database in such a way that it just reads from the Excel sheet at model runtime. So it reads the truck details at model runtime, and it schedules the trucks based off this in time column. So here I've shown like a sample VTS data containing the unique ID of the truck, dock number, which dock it's supposed to go to, the in time when it entered the plant, and the dock in time as well as dock out time. We will get our tat time from this. And also the trolley information is stored in Excel as well. So we have what part it carries, basically what trolley it is, and the number of trolleys it has, and the start time, like at what time of the day it starts. Like here, for instance, four-wheeler body starts at 8:38 a.m. So this time is the trigger for which the model should start generating these trolleys, and they end at 5:05 p.m. So like that, we have various trolleys over here, and we also have the trip repeat, like how often should they keep generating. In this case, like how often do they keep entering into the plant? circulating around the plant. So these four colors actually represent the destination, like where they're supposed to go, and each color has a different process flow, like movement flow. They follow a different path, and all this has been modeled in AnyLogic. Now, what approach like in AnyLogic did we take in terms of like what libraries did we use and all that? So it was a mixture of PML process modeling library and material handling library. And that in this case, the trucks and trolleys were made as transporters. Now, why as transporters? Well, we needed it for easier routing and mainly for collision detection and providing with access restrictions. Now, why do we need access restrictions? So we have created several rectangular nodes, okay, and we have defined them as access zones. Now, the yellow squares that you see over here, there actually are access zones. Now, why do we need them? Basically, we don't we want to simulate the traffic in the plant. So we have given an access restriction in each of these nodes, saying like only one or two transporters, depending on which location transporter, whether it be a trolley or a truck, must wait outside until it passes through the node. Now, there were also certain cases where we needed some more custom logic, like we had to add a virtual gate over here. Like I will get to this later. So we had to add custom logic as to when the truck could enter. So exact process flow was made, like I had told that earlier, like exact process flow was made, like the truck reversing and getting into the dog. Now, moving on to the next slide. This is like the model logic which I had used. It might be very naive. I hope that's fine. But if so, the logic which I used was like first the truck uh, gets generated, the agent gets generated. Then the model will check if the the dock is occupied or not. If not, then send it to its designated parking buffer. If it's not occupied, then send it to the dock. If the dock is, sorry, if the dock is occupied, send it to its designated parking buffer. Otherwise, it can go ahead and enter the plant. Now, if, for example, it enters the plant, it will then follow that exact process flow which I have defined for it, and it will go to the dock. Once it reaches the dock, I have added a delay over there. So this delay contains the dock turnaround time. So this delay will just simulate the loading and the unloading process. Now, for instance, for example, if the dock is occupied, then it must wait outside or in its designated parking buffer, which I have defined in the model. And there, then again, I have defined a delay over here. So now how is this delay calculated? This delay calculates, first of all, it checks how much time is left for the truck inside the plant to leave the dock. Let's say, for instance, dock number 5 is occupied and the truck needs to enter the plant, but it can't since it's occupied by another truck. So the system will then check, okay, how much time is left for the truck already present in the dock, 5, is left for unloading. Like how much time is left? Let's say 15 minutes. So then the delay will be given as 15 minutes for the truck to wait in its parking buffer. Now, if there are multiple trucks waiting in line, then the system will also check for this and it will automatically take a cumulative of all the loading and unloading times as well as the truck that is already inside the plant. So it will basically like chain up the delays. Like this is how I have approached this. Now, once it reaches the dock and its loading and unloading process is over, it follows a similar process for exiting the plant. And once they leave, the agent just gets gets thrown into a sink and gets destroyed over here. Now, for the trolleys, I have used several sources as they have different start times and as well as different number of trolleys as well. So I have used several sources, but the concept is still the same. Like I have defined like where they need to go with move by transporter block, and they'll just go there and then return back to their gate. So these trolley spawns and all this kind of movement flow was needed to give this a dynamic environment so that like we can add to the complexity of the model and more variability to it. So once again, just a glimpse of all the agents that we had used over here. So this is the dock agent, its parameters and the variables. This is the trolley agent, and this is the truck agent. So they have several things that were needed to make the flow, like what is the dock number of the dock? We obviously need that. And for the truck, we needed the dock number, meaning what dock it had to go to, which supplier is it from, what's its unique ID, and all that. Now, I have a demo video for this, but I'll just brief you through what the scenario is. So we have created like a scenario, like a process flow of what should happen. Now, if you see here, uh, in this area of the plant, there is a thing which is happening. So the truck which needs to enter the plant, they need to enter and reverse straight through this line and into this dock over here. So there are two docks present over here, and these docks need to be entered while they're in reverse. Like they need to reverse enter into the dock. And there's another issue with this. So the trolleys which are coming are actually coming in the opposite direction to the truck. They're coming from up top over here. So this creates a safety hazard, and the current process flow in the plant is to only let either one of them to pass. So if the truck, for instance, spots a trolley which is coming in the oncoming direction, then the truck must wait until the trolley crosses it and then goes ahead. So what I had done for this in the model, if you see here, this is a truck right over here, and this is a trolley over here. And I have defined a rectangular node of this size. It's also an yellow, so bear with me on that. Of this size. And what the system does is, like if a trolley is entering in the oncoming direction, meaning if it's coming from top to bottom in our case, then I have added a virtual gate over here, which remains closed, like a rectangular node. So this gate will remain closed, and we can also see that I have defined a variable to see how many trolleys as such are coming over here. Here we can see that there are two trolleys as such. And I've also defined a function gate control over here, which opens and closes this node accordingly. So I will show you a demo next of whatever I just told. So here we can see that the green section is the section which must be clear of any oncoming trolleys before the truck can reverse into the dock over here. So I'll just play it. Yeah, also the model sped up. That's why it looks like a lot of stuff is happening in the plant. So here we can see that truck and this trolley, the truck is waiting for the trolley to cross, and as soon as it crosses the green line, the gate opens and it's able to go and reverse into it. I can play that one more time just so we can see it clearly. Now the truck reverses over here, but then there's a trolley already coming. Since this creates a safety hazard, the gate remains closed. It waits for all the trolleys to pass. If you notice that it does not do the same for the out, like the trolley is going back, like along the direction of the truck that is reversing. It does not close the gate. It only closes the gate only if the trolley is coming in the oncoming direction, like in the opposite direction. So these are the code blocks which logic which I used. So pretty simple. So I just check in the rectangular node whether the agent that is entering is a trolley or not. If it is a trolley, I'll also have a parameter that is checking if it is heading heading towards its destination or no. So since it's heading towards its destination, then obviously it must be oncoming to the trucks. If it is heading back after dropping off the material at the destination, then the parameter onward will be false. So I'm just checking when it enters the node whether it's a trolley and whether the parameter is true or not, onward parameter. If so, then I'm just increasing this counter by 1. And if the counter is not equal to 0, that means there is a trolley, oncoming trolley present in that node, and I'll just close the gate over here, the node basically. And on exit, I just do the opposite. I just decrement the counter. So what's the output from this? Uh, Here we can see that we had used a month's data for this from VTS, and we have had observed for this particular data set that docs number 3, 15, 12, and 2 were being heavily utilized in the sense like they were being more utilized compared to other docs. And some other docs in the sense like 16, 14, and 13. So if you see over here, for example, doc number 16, it's just being used 0.04%, whereas doc number 3 is being used 0.82%. Now, how did I derive this utilization? Just a simple logic, just checking how much time has passed versus how much time the dock was occupied in this time. So it's pretty simple. And we can see, coming back to the data, we can see that dock number 3 has 82% of utilization compared to dock 16, which is like only 4%. And this model, which I made, has given this visibility to the logistics team. They were able to see, okay, how much pretty sure they would have been aware that dock number 16 was being underutilized, but this helped them to bring it to a quantitative value. Like they knew how much it was being underutilized. So we have these charts over here, and the model also outputs to the Excel file, back to the Excel file, these columns in LO. So we have in time, model in time, and the model doc in time, doc out time, and out time. So all these data is coming from the model. The only thing that we collect from VTS is the in time. We don't collect the out times at all. The out times are coming directly from the model as per the defined process flow. Now, these data points will actually give us, like for instance, this model dock in time will give us how much time it took for the truck to go from the gate to the dock. So why is this even needed from the model, right? Because if it is a defined process flow, it should be fixed, right? It should be like 10 seconds for this dock and all. But actually, this is useful in the case where we need to see whether to identify any congestion or traffic in the plant. If the traffic is very high, then the truck will take more time to go from gate to the dock, since it will encounter lots of other trucks as well as trolleys in the way. If the traffic around that time is pretty low, then it should go from the gate to the dock quickly. So this column, for instance, will give you insights on that. So we likewise get the model out time and the total takt time, how much time it spent inside the plant, and whether it was waiting or no for whatever reason, whether dock was occupied or there was congestion or something like that. So we have those waiting times as well, and they come directly from the AnyLogic model. Now, what inferences do we have from the output that we got? Now, this helped our Haridwar plant logistics team to plan out future truck schedules from the suppliers and distribute the load evenly, the truck load. No pun intended over there, I had to put that. Anyways, so what I mean by that is rather than unevenly or like not thinking too much about it, like if we just schedule the trucks as per like how we want, like the material requirements and all, there can be a chance that multiple trucks can arrive, and these trucks, like even though it's not needed for multiple trucks to arrive, they can create unnecessary congestion in the plant because they will then just enter the plant and just like wait over there until the dock becomes free, rather if they were distributed evenly throughout the day. So that's why the schedule is like very important, and the model helped give them visibility in this. So this in turn led to better material availability on the TCF lines, and they were also able to balance out the dock utilization, like I told earlier. And once the material shortages were reduced, we also incurred lesser losses because of that on the line, and we were able to improve our capacity. So based on this data as well, we could better plan out the schedule of trucks, like what trucks should come at what time, like exactly. And this also led to like a huge decrease in average wait times for our trucks. Like they didn't spend as much time as before, like waiting in the parking buffer and all that. So now
Nihan,
this in turn,
sorry, I have to cut you off over there. Unfortunately, we couldn't get to the last part about the future scenarios, but we have got the results that you have achieved so far. We just unfortunately ran out of time.
yeah,
And thank you so much for your presentation today. It was really good. And
yeah,
you had a couple more slides about the future, which we will show later.
yeah, it's okay, it's okay. Maybe
And
people can get a
the
glimpse.
great last slide about your Batman edition for the future.
Yeah, I want to show this. Like we just recently launched this variant of our electric vehicles, so I think it
Yeah.
looks pretty cool. I just want to show.
It looks amazing. Yeah, really, really nice. Okay, thank you. We hope to see you again next year.